July 10, 1860, Donner Pass, California. The European trained railroad engineers' assessment would prove catastrophically wrong within a decade. American steam locomotives, climbing mountain grades that violated every principle of 19th century railroad engineering. Through the granite peaks of the Sierra Nevada, black smoke poured from locomotives hauling loads that European mathematics said were physically impossible. No electric assistance, no distributed power systems, no modern computerized traction control. Yet they pulled 1,200 tons of freight-up gradients that today's diesel-electric engines require multiple helper locomotives to conquer. European engineers had calculated the tractive effort equations. Steam locomotives could not generate sufficient pulling force for meaningful tonnage on grades exceeding 2.5%. The Sierra Nevada rose 7,000 feet above sea level, with sustained inclines that should have stopped any steam engine dead in its tracks. But the Americans were operating with mechanical principles the Europeans had dismissed as theoretically unsound. Direct steam-to-wheel power transmission, maximum torque at zero speed, constant pulling force rather than constant horsepower. 7,000 miles from European railroad academies, the most decisive transportation breakthrough in American history was revealing itself. Not in superior metallurgy, not in advanced boiler design, but in understanding the fundamental physics that made steam power perfectly suited for the impossible. The invitation arrived at Theodore Judah's Sacramento office on a sweltering July morning in 1860, written in the careful script of Dutch flat storekeeper Doc Strong. "Come see the pass for yourself," it read simply. "Bring your surveying instruments." Judah had spent 3 years evangelizing his Transcontinental Railroad vision to anyone who would listen, earning him the nickname Crazy Judah from Sacramento's business community. The European-trained engineers who dominated American railroad construction had already delivered their verdict. The Sierra Nevada represented an impenetrable barrier to steam locomotion. The mathematics seemed ironclad. Donner Pass rose 7,000 feet above sea level, creating sustained gradients averaging 2.5% over distances that would test any steam engine's limits. European railroad doctrine, established through decades of flat-terrain construction across England and the continent, held that grades exceeding 1% were commercially impractical. The textbooks were explicit. Steam locomotives generated insufficient tractive effort to pull meaningful tonnage up such inclines. A locomotive might struggle up a short hill, but the Sierra Nevada demanded sustained climbing over dozens of miles through solid granite. Judah understood the skepticism. His own engineering education had emphasized the same principles. Steam engines developed. Power through the expansion of heated water vapor in cylinders, which drove pistons connected to driving wheels through mechanical linkages. The force available for pulling, termed tractive effort, was limited by boiler pressure, cylinder dimensions, and wheel diameter. European engineers had calculated these limits precisely, and their mathematics appeared to prove that mountain railroading was fundamentally impossible with existing technology. But Judah possessed something his European counterparts lacked: an understanding of steam power's unique mechanical characteristics. Unlike the diesel-electric locomotives that would dominate 20th century railroading, steam engines developed their maximum pulling force precisely when trains needed it most, at zero speed. This starting tractive effort represented the locomotive's peak performance, declining as speed increased. European engineers viewed this as a limitation, but Judah recognized it as the perfect solution for mountain railroading. The physics were counterintuitive. A steam locomotive standing motionless could exert tremendous force against the rails through its driving wheels. As the train began moving, steam pressure remained constant while mechanical advantage decreased. But the initial breakthrough required maximum force. Once a heavy train was rolling, momentum helped maintain motion even on steep grades. Steam locomotives didn't need to accelerate rapidly up mountains. They needed to pull steadily at slow speeds, exactly what their torque characteristics provided. Doc Strong's invitation represented validation from an unexpected source. The Dutch flat storekeeper had spent 15 years traversing Sierra Nevada passes, observing seasonal weather patterns and geological formations that affected transportation routes. His practical knowledge of mountain terrain complemented Judah's theoretical understanding of railroad engineering. Strong had identified what he called the easy, continuous rise a steam locomotive needed, a route that avoided the brutal switchbacks and impossible gradients that had defeated previous surveys. When Judah finally climbed Donner Pass with Strong in late July, the revelation was immediate. European engineers had surveyed the Sierra Nevada looking for the gentle grades that characterized their homeland railroads. They found only forbidding slopes and declared mountain railroading impossible. But Strong showed Judah something different, a natural pathway that rose steadily but manageable, following ridge lines and valley contours that steam locomotives could traverse with loads intact. The breakthrough came from recognizing that American conditions demanded American solutions. European railroads connected established cities across relatively flat terrain, optimizing for speed and passenger comfort. The Transcontinental Railroad faced different challenges, hauling freight across wilderness terrain where gradients mattered more than velocity. Steam. Locomotives were perfectly suited for this application, provided engineers abandoned European prejudices about acceptable grades. Judah's excitement was infectious but also isolating. Sacramento's merchant community viewed his passion as evidence of impractical dreaming rather than engineering insight. They had invested in local railroad projects that generated predictable returns, not speculative ventures that challenged fundamental assumptions about steam power. Bankers who might finance warehouse construction or riverboat operations saw only risk in Judah's mountain railroad scheme. The irony was profound. Steam technology had reached remarkable sophistication by 1860, with locomotives routinely hauling heavy freight trains across thousands of miles of American prairie and woodland. The Baltimore and Ohio Railroad operated steam engines that could pull 500 tons on level track. The Pennsylvania Railroad's finest locomotives generated starting tractive effort exceeding 10,000 pounds. Yet established engineering wisdom insisted these same machines were helpless against mountain grades. Judah understood that proving his theory would require more than mathematical calculations or surveying reports. He needed investors willing to gamble on revolutionary engineering, contractors capable of blasting through granite, and locomotives designed specifically for mountain service. Most critically, he needed to convince skeptics that steam power's limitations were imaginary rather than physical. The technical specifications were encouraging. Central Pacific's planned 440 locomotives would weigh 40 to 46 tons and generate starting tractive effort between 8,000 and 12,000 pounds, with boilers operating at 250 pounds per square inch. Cylinders measuring 16 inches by 24 inches would provide the displacement necessary for sustained mountain climbing. These were not experimental machines, but proven designs adapted for Western conditions. By autumn of 1860, Judah had secured the support he needed from an unlikely quartet of Sacramento merchants: Leland Stanford, Collis Huntington, Mark Hopkins, and Charles Crocker. These practical businessmen lacked engineering training but possessed the entrepreneurial instinct to recognize transformative opportunity. They would become known as the Big Four, though their relationship with Judah would prove both essential and ultimately tragic. The stage was set for the most ambitious engineering project in American history. Steam locomotives would attempt what European expertise declared impossible, conquering a mountain range through nothing but mechanical advantage, skilled labor, and stubborn determination. The first Central Pacific locomotive arrived at Sacramento's waterfront in February 1862, shipped in components around Cape Horn after a 4-month ocean voyage. The Governor Stanford, a Campbell-built 440 design, represented everything Judah believed about steam power's mountain climbing potential. Weighing 43 tons with driving wheels 60 inches in diameter, the locomotive embodied mechanical principles that European engineers consistently misunderstood. Steam locomotives operated on fundamentally different physics than the diesel-electric machines that would later dominate railroading. Where diesel engines generated constant horsepower with variable torque, steam power provided constant torque with variable horsepower. This distinction proved crucial for mountain railroading, though most engineers failed to grasp its significance. The Governor Stanford cylinders measured 16 inches by 24 inches, designed to convert 250 pounds per square inch of boiler pressure into rotational force at the driving wheels. The mathematics were straightforward, but revolutionary. Starting tractive effort equaled cylinder pressure multiplied by piston area, multiplied by stroke length divided by driving wheel radius. For the Governor Stanford, this calculation yielded approximately 10,000 pounds of pulling force when motionless, exactly when trains needed maximum power to overcome inertia and begin climbing steep grades. As speed increased, effective tractive effort decreased, but mountain trains rarely exceeded 15 miles per hour on serious grades. Judah recognized that this torque characteristic made steam locomotives perfectly suited for sustained mountain climbing. Unlike diesel engines that required electrical transmission systems to convert constant horsepower into variable pulling force, steam power delivered mechanical energy directly from cylinders to wheels through connecting rods and driving mechanisms. No power was lost through electrical conversion, no complex transmission systems introduced failure points, and no computerized controls were needed to manage traction. The Central Pacific's engineering staff, led by Assistant Engineer Lewis Clement, began testing the Governor Stanford on Sacramento Valley grades during the spring of 1862. Initial trials confirmed Judah's calculations. The locomotive could pull loads that European mathematics declared impossible, provided the train maintained steady speed rather than attempting rapid acceleration. A consist of 12 freight cars weighing 450 tons posed no challenge on level track, and the same train climbed 2% grades without difficulty. But Sacramento Valley tests offered no preview of Sierra Nevada conditions. Donner Pass would demand sustained climbing over distances exceeding 20 miles, with grades averaging 2.5% and individual sections reaching 4%. Materials would need transport over these same grades, rails weighing 560 pounds each, locomotives weighing 40-plus tons, construction equipment, explosives for tunnel blasting, and supplies for thousands of workers. The railroad would need to build itself up the mountain, carrying its own construction materials on grades that skeptics insisted were unclimbable. The breakthrough came from understanding steam power's mechanical elegance. Steam engines developed torque through direct mechanical connection between pistons and driving wheels, with no intermediate transmission systems to absorb power or introduce complexity. When steam expanded in the cylinders, connecting rods transferred that force immediately to the rails through friction between steel wheels and steel track. This direct power transmission meant that steam locomotives could utilize every pound of tractive effort for pulling loads, unlike diesel-electric systems that lost energy through multiple conversion stages. European railroad experience had established benchmarks that seemed mathematically definitive. A typical English freight locomotive could pull approximately 20 times its own weight on level track, a 40-ton engine hauling 800 tons of freight cars. But mountain grades reduced this ratio dramatically. European calculations suggested that a 2% grade would cut hauling capacity by 60%, making profitable freight operation impossible over mountain passes. American testing revealed different results. The Central Pacific's locomotives could indeed pull reduced loads on steep grades, but the reduction was less severe than European formulas predicted. More importantly, American freight operations emphasized ton miles rather than speed, making slower mountain transit commercially viable. A locomotive pulling 300 tons over Donner Pass at 8 miles per hour generated more revenue than the same engine pulling 600 tons across flat terrain at 12 miles per hour, provided the grade didn't require helper locomotives. The physics of steam traction offered additional advantages that European engineers had overlooked. Steam locomotives could operate at partial throttle settings, reducing steam consumption while maintaining steady pulling force. Mountain railroading demanded precisely this characteristic, consistent power output rather than maximum performance. Firemen could adjust combustion rates to match grade requirements, burning less coal on moderate slopes while maintaining boiler pressure for steep sections. Central Pacific's mechanical engineers began modifying standard locomotive designs for mountain service during 1863. Boiler modifications included larger fireboxes to maintain steam generation during sustained climbing, improved draft systems to enhance combustion efficiency at slow speeds, and reinforced frames to handle the stress of constant heavy pulling. Cylinder modifications included larger bore dimensions to increase starting tractive effort and improve valve timing to optimize steam utilization at low speeds. The most significant innovation involved understanding how steam locomotives could work together on heavy grades. Rather than requiring specialized helper engines like modern railroads, steam power could be distributed throughout a train consist. Multiple locomotives could operate in tandem, with each engineer coordinating throttle and brake applications to maintain steady train movement. This distributed power concept would prove essential for hauling construction materials over Sierra Nevada grades. Testing continued through the summer of 1863 as Central Pacific prepared for serious mountain construction. The Governor Stanford regularly pulled construction trains up experimental grades built along the American River Canyon, validating calculations about steam power's mountain capabilities. Each successful test disproved another aspect of European orthodoxy about railroad engineering limitations. By autumn, Judah's mechanical theories had evolved into proven engineering practice. Steam locomotives could indeed conquer mountain grades that European expertise declared impossible, provided American engineers abandoned European prejudices about acceptable operating parameters. The Transcontinental Railroad would succeed through mechanical principles that formal engineering education had overlooked: direct power transmission, maximum torque at zero speed, and the elegant simplicity of steam technology applied to uniquely American transportation challenges. Construction began in earnest during the spring of 1863, as Central Pacific crews pushed rails eastward from Sacramento into the foothills of the Sierra Nevada. The real test of steam power's mountain capabilities would come not from theoretical calculations, but from the brutal reality of hauling construction materials up grades that increased with every mile. Rails weighing 560 pounds each, cross ties cut from Sierra pine, and locomotives themselves would need transport over the same grades they were built to conquer. The Governor Stanford proved its worth immediately, pulling supply trains up initial grades that European engineers had dismissed as commercially impossible. By summer, the locomotive was regularly hauling 15-car consists weighing 400 tons up 2% grades at steady 8-mile-per-hour speeds. Fireman James Campbell developed techniques for maintaining steam pressure during sustained climbing, learning to anticipate grade changes and adjust firing rates to keep boiler pressure constant at 250 pounds per square inch. But the Sierra Nevada's most formidable challenge lay ahead: Summit Tunnel, a 1,659-foot bore through solid granite directly under Donner Pass. This single tunnel would determine whether steam locomotives could truly conquer mountain railroading or whether European skepticism was justified. The tunnel required precision blasting through rock formations so hard that steel drill bits dulled after penetrating mere inches. Progress measured not in feet per day, but inches per shift. Chinese work crews, recruited from Guangdong province and comprising 90% of Central Pacific's workforce, developed innovative blasting techniques that combined traditional Asian engineering methods with American black powder technology. Working in 3 shifts around the clock, 6 days per week, they advanced through granite using hand drills, sledgehammers, and carefully calculated explosive charges. Each blast removed perhaps 2 feet of rock face, requiring immediate removal of debris before the next drilling cycle could begin. The logistics were staggering. Every pound of black powder, every drill bit, every timber support, and every tool needed transport up grades that climbed steadily towards 7,000 feet elevation. Steam locomotives hauled these materials in consists that would have been impossible on European railroads, demonstrating daily that American steam power could accomplish what established engineering wisdom declared impractical. Louis Clement, inheriting Judah's engineering responsibilities after the visionary's death from yellow fever in November 1863, faced the challenge of completing construction while maintaining the technical innovations that made mountain railroading possible. Clement lacked Judah's evangelical passion, but possessed practical engineering skills and the political acumen necessary to work with the Big Four investors who controlled project financing. The Summit Tunnel presented engineering challenges that went beyond simple excavation. The bore needed precise alignment to maintain railroad grades through the mountain, requiring surveying accuracy measured in fractions of inches over distances exceeding half a mile. Chinese crews worked from both ends simultaneously, meeting in the middle with alignment errors of less than 2 inches, a testament to American surveying techniques and Asian craftsmanship working in combination. Steam locomotives proved essential, not just for hauling materials, but for powering construction equipment. The Central Pacific mounted steam-powered air compressors on flat cars, using locomotive boilers to generate compressed air for pneumatic drills that could penetrate granite faster than hand tools. This innovation represented practical American engineering at its finest, existing steam technology adapted for entirely new applications through mechanical ingenuity rather than theoretical complexity. Winter conditions in the Sierra Nevada tested steam power's reliability under extreme circumstances. Locomotives operated in temperatures that froze exposed water pipes and made steel components brittle. Snow accumulations exceeding 20 feet required constant plowing to keep rails clear. Yet steam engines continued operating when other technologies would have failed, their massive boilers providing both motive power and heating for crews working in impossible conditions. The Chinese workers' dedication became legendary throughout construction. They rappelled down cliff faces on rope baskets to place explosive charges in locations no American worker would attempt. They lived in camps at 7,000 feet elevation through Sierra winters that killed unprepared travelers. They maintained work schedules that averaged 12 hours per day, 6 days per week, for wages that represented financial freedom compared to conditions in Guangdong province. By 1866, Summit Tunnel was nearing completion despite geological challenges that had delayed progress for 2 years. The bore required timber supports every few feet to prevent cave-ins, with each support beam hauled up mountain grades by steam locomotives that demonstrated their superiority over animal-powered transportation. A horse-drawn wagon might carry 2 tons up moderate grades. Steam locomotives routinely pulled 20 times that load up steeper inclines. The tunnel's completion in late 1866 represented vindication of every principle Judah had advocated about steam power's mountain capabilities. Rails laid through the bore maintained precise grades that allowed loaded freight trains to traverse the summit without helper locomotives. The engineering was so sound that the same alignment would carry freight traffic for more than a century, proving that American railroad construction had achieved standards equal to anything European expertise could provide. Steam locomotives immediately began hauling construction materials through Summit Tunnel and down the eastern slopes of the Sierra Nevada, demonstrating that mountain railroading was not only possible, but profitable. Trains that had struggled up the western approach could now descend eastern grades while maintaining safe speeds through careful brake application and throttle management. The breakthrough had profound implications for American transportation. Steam power had conquered the continent's most formidable geographical barrier through mechanical principles that European training had dismissed as inadequate. Direct power transmission from cylinders to driving wheels, maximum torque at zero speed, and the elegant simplicity of steam technology had proven superior to theoretical objections based on outdated assumptions about railroad operating parameters. Construction crews pushed eastward across Nevada's high desert, laying track at unprecedented rates while steam locomotives hauled supplies over distances that would have been impossible with animal-powered transportation. The Transcontinental Railroad was becoming reality through American engineering innovation applied to uniquely American challenges. The race intensified during 1868 as Central Pacific crews descended the eastern slopes of the Sierra Nevada while Union Pacific construction gangs pushed westward across Wyoming Territory. Both railroads operated under federal legislation that provided land grants and construction subsidies based on miles of track completed, creating fierce competition between the two companies. Steam locomotives had proven their mountain climbing capabilities. Now they would demonstrate their capacity for sustained high-speed construction across desert terrain. Central Pacific's advantage lay in the Chinese workforce's systematic efficiency and the steam-powered logistics system that supplied materials faster than any competing transportation method. Louis Clement had refined construction techniques through 3 years of mountain building, developing specialized trains for different aspects of railroad construction. Grading crews worked ahead of track layers, using steam-powered scrapers and dump cars to prepare roadbeds. Bridge gangs followed with prefabricated timber spans hauled by locomotives that could position heavy structural components with precision impossible using animal power. The Big Four pushed for maximum construction speed to capture federal subsidies and establish territorial claims before Union Pacific crews could advance further west. Charles Crocker, supervising construction operations, established quotas that demanded track laying rates previously considered impossible. His teams would lay rails, position crossties, and spike track while steam locomotives continuously supplied materials from supply bases hundreds of miles distant. On April 28, 1869, Central Pacific achieved what became known as the 10-mile day, laying 10 miles and 56 feet of new railroad track between sunrise and sunset. The feat required coordination between multiple specialized crews, graders preparing roadbed, bridge builders spanning small ravines, track layers positioning rails and cross ties, spike drivers securing track to roadbed, and ballast crews stabilizing the completed railroad. Steam locomotives hauled supplies to each crew simultaneously, demonstrating logistical capabilities that European railroad construction had never achieved. The engineering precision was remarkable. Each mile of new track required 400 rails weighing 560 pounds each, plus 2,600 cross ties, 30,000 spikes, and tons of crushed stone ballast. Steam locomotives delivered these materials to exact locations along the construction route, timing arrivals to match crew progress. A single delay could halt the entire operation, yet Central Pacific maintained continuous supply flow across distances that would have defeated horse-drawn transportation. Individual rails weighing over 500 pounds required careful handling to prevent injury and maintain construction speed. Chinese crews developed techniques for positioning heavy rails using coordinated lifting that minimized individual strain while maintaining steady progress. Each rail needed precise alignment with existing track and exact spacing to ensure smooth locomotive operation. Spike drivers working behind the rail crews secured each connection with 4 spikes per rail end, driving 30,000 spikes during the 10-mile day alone. The completed track immediately underwent quality testing that validated construction standards. A locomotive operated over the new rails at 40 miles per hour, subjecting every joint and spike to forces that would reveal any construction defects. The track performed flawlessly, proving that rapid construction could achieve quality standards equal to slower traditional methods. Steam power had enabled both speed and precision in railroad construction. Union Pacific observers watched Central Pacific's progress with growing alarm. Their own construction techniques, developed across flat prairie terrain, could not match the efficiency of steam-powered logistics systems refined through Sierra Nevada mountain building. Union Pacific crews relied heavily on animal-powered transportation that limited supply capacity and reduced construction speed. Their locomotives, optimized for prairie operations, lacked the pulling power that Central Pacific engines had developed through mountain service. The competition revealed fundamental differences between Eastern and Western railroad construction philosophies. Union Pacific followed established practices that prioritized cost control and conventional engineering. Central Pacific had developed revolutionary techniques through necessity, creating construction methods that maximize steam power's unique capabilities. These innovations gave Central Pacific decisive advantages in the final construction push toward Promontory Summit. Financial pressures mounted as both railroads approached their meeting point. The Big Four had invested everything in Central Pacific's success, mortgaging personal assets and business holdings to maintain construction financing. Federal subsidies provided essential funding, but payments depended on completed mileage, creating pressure to maintain construction speed regardless of obstacles. Every mile built meant immediate cash flow. Every delay represented potential bankruptcy. The irony was profound. Theodore Judah had died before seeing his transcontinental vision approach completion, yet his engineering principles were proving decisive in the final construction phase. Steam locomotives designed for mountain service excelled at desert construction, hauling heavy loads at speeds that enabled unprecedented track laying rates. Judah's understanding of steam power's mechanical advantages had evolved into practical construction techniques that no competing technology could match. Central Pacific's success attracted national attention from railroad industry observers who had dismissed Western construction capabilities. Eastern engineers who had predicted failure now studied Central Pacific's methods, recognizing innovations that challenged fundamental assumptions about railroad construction. Steam-powered logistics, Chinese workforce efficiency, and systematic construction techniques. Developed through Sierra Nevada, challenges had created new standards for American railroad building. The approaching completion of the Transcontinental Railroad represented vindication of every principle Judah had advocated about American engineering innovation. Steam locomotives had conquered mountain grades that European expertise declared impossible, powered construction at rates that established industry observers considered unrealistic, and demonstrated reliability under conditions that would have defeated less robust technologies. The mechanical elegance of steam power, applied through American ingenuity to uniquely American challenges, was creating transportation infrastructure that would transform continental commerce. As construction crews from both railroads converged on Promontory Summit, Utah Territory during the spring of 1869, the outcome was no longer in doubt. Steam locomotives had proven their supremacy over geographical obstacles and construction challenges that had seemed insurmountable just 9 years earlier. The Transcontinental Railroad would succeed through American mechanical innovation that refused to accept European limitations as permanent constraints on transportation progress. May 10, 1869 dawned clear and cold at Promontory Summit, Utah Territory, as two locomotives approached each other across a gap of rails that represented the culmination of the most ambitious engineering project in American history. Central Pacific's Jupiter, a gleaming 440 locomotive weighing 42 tons, faced Union Pacific's number 119 across a ceremonial distance that symbolized the conquest of an entire continent. The moment validated every principle Theodore Judah had advocated about steam power's mountain climbing capabilities and proved that American engineering innovation could accomplish what European expertise had dismissed as impossible. The Jupiter embodied mechanical principles that had confounded railroad establishment thinking for nearly a decade. Its cylinders measured 16 inches by 24 inches, generating starting tractive effort of 11,000 pounds through direct mechanical connection between steam expansion and driving wheel rotation. No electrical transmission systems absorbed power, no complex controls managed traction distribution, and no helper locomotives were needed for mountain service. Steam technology had conquered the Sierra Nevada through elegant mechanical simplicity that diesel-electric power would struggle to match even a century later. Leland Stanford, representing Central Pacific's board of directors, prepared to drive the ceremonial golden spike that would complete the Transcontinental Railroad. The irony was profound. The man who had once dismissed Judah's mountain railroad as financially impractical now presided over its triumphant completion. Steam locomotives had generated profits that exceeded the Big Four's most optimistic projections, hauling freight over grades that European mathematics declared commercially impossible. The Transcontinental Railroad was succeeding precisely because American engineers had abandoned European prejudices about steam power's limitations. The engineering legacy was already apparent to industry observers who had traveled from across the nation to witness the ceremony. Central Pacific's locomotives routinely pulled loads up Sierra Nevada grades that required multiple helper engines on modern railroads. The 440 steam engines accomplished through mechanical advantage what 21st century diesel-electric locomotives achieved through computerized distributed power systems. Starting tractive effort reaching maximum when motionless provided exactly the pulling force needed for mountain railroading, while constant torque characteristics maintained steady train movement on sustained grades. Telegraph operators prepared to transmit news of the completion across a continental communications network that paralleled the railroad's achievement. The Transcontinental Railroad represented more than transportation infrastructure. It demonstrated American technological capabilities that could compete with established European engineering. Steam power had proven superior to animal-powered transportation, not through theoretical innovation, but practical application of mechanical principles that formal engineering education had overlooked. The completed railroad immediately began generating revenue that justified every investment the Big Four had made, despite years of financial uncertainty. Freight trains hauled California agricultural products eastward, while manufactured goods moved west, creating commerce flows that transformed continental economics. Steam locomotives that had struggled up Sierra Nevada grades during construction now pulled profitable consists over the same routes, demonstrating that mountain railroading was not merely possible, but highly lucrative. Chinese workers who had blasted Summit Tunnel through 1,659 feet of solid granite watched the ceremony from respectful distances, their contributions largely unrecognized by contemporary observers, despite comprising the workforce that made transcontinental completion possible. Their innovative blasting techniques and tireless work ethic had proven that American railroad construction could achieve quality and speed standards that European projects rarely matched. Steam locomotives had provided the logistics capabilities that supported their efforts, hauling materials and supplies over grades that would have defeated animal-powered transportation. The technical specifications validated Judah's original calculations about steam power's mountain capabilities. Central Pacific locomotives weighing 40 to 46 tons regularly pulled consists totaling 1,200 tons, up grades averaging 2.5%. European engineers had predicted these loads were impossible, yet American steam technology accomplished them routinely through direct mechanical power transmission that maximized tractive effort efficiency. The physics were straightforward. Steam expansion in cylinders converted immediately to rotational force at driving wheels, with no intermediate systems to absorb energy or introduce complexity. Louis Clement, who had inherited Judah's engineering responsibilities and successfully completed the Sierra Crossing, understood that the Transcontinental Railroad success would reshape American transportation forever. Steam locomotives had proven their superiority over geographical obstacles that had seemed insurmountable, establishing construction techniques and operating practices that would influence railroad development for decades. The mechanical principles that conquered the Sierra Nevada would enable railroad expansion across other mountain ranges, opening Western territories to settlement and commercial development. Modern railroad observers would later marvel at 19th century steam power's mountain climbing capabilities. 21st century freight railroads required helper locomotives, distributed power systems, and computerized traction control to haul heavy trains over grades that 1860s steam engines conquered with mechanical elegance. The EMD SD70AC T4 locomotives that dominated modern mountain railroading generated 4,600 horsepower, but still needed multiple units for loads that single steam engines handled routinely. The fundamental difference lay in power characteristics that diesel technology could never replicate. Steam locomotives developed constant torque with maximum pulling force at zero speed, exactly when trains needed greatest tractive effort. Diesel-electric locomotives generated constant horsepower with variable torque, requiring complex transmission systems to manage power distribution. Steam power's mechanical directness provided advantages that electrical technology obscured through conversion losses and control complexity. As the Golden Spike ceremony concluded, and the Jupiter touched pilots with number 119, the Transcontinental Railroad's completion represented vindication of American engineering innovation that refused to accept European limitations as permanent constraints. Steam locomotives had conquered the Sierra Nevada through mechanical principles that formal training had dismissed, proving that practical ingenuity could accomplish what theoretical expertise declared impossible. The age of transcontinental transportation had begun through steam power's triumph over geographical obstacles and engineering skepticism that had underestimated American technological capabilities. The railroad's success would inspire similar projects across the American West, each depending on steam locomotives' unique ability to generate maximum pulling force precisely when mountain grades demanded it most. The mechanical legacy of 1869 would endure long after steam power gave way to diesel technology, establishing engineering principles that recognized no obstacle as truly insurmountable when American innovation confronted seemingly impossible challenges.